Let's explore C++ templates. Templates enable type-independent programming in C++, allowing developers to write functions and classes that work with any data type without sacrificing type safety or performance. Templates offer several key benefits. You can write code once and use it with multiple types. Templates provide type safety at compile time, meaning errors are caught early. There's no runtime overhead, ensuring efficient execution. Templates enable generic programming, promoting code reusability. Finally, templates reduce code duplication, making your code cleaner and easier to maintain. Let's look at an example. Without templates, you might need separate functions for each data type, such as maxint for integers and maxDouble for doubles. With templates, you can create a single max function that works for all types. The code shows both approaches for comparison. Function templates allow you to define a function that can work with any data type. The compiler generates the appropriate function for each type used. Here's the function template syntax. The keyword template, followed by type name, and a placeholder type name like t, defines a template function. You can then use t as a data type within the function. For example, the swap function takes two references of type t and swaps their values using a temporary variable. When you use the template function like swap with integer variables x and y, the compiler generates a swap function specifically for integers. Templates can have multiple type parameters to create even more flexible functions. Here is an example. The code shows a function with multiple template parameters, t and u. The add function takes arguments of type t and u and returns their sum. The return type is automatically deduced. You can use the template with different types, such as integers and doubles. The result1 variable stores the result of adding number and number, which are integers. The result2 variable stores the result of adding number, which is an integer, and val, which is a double. Template specialization allows you to provide a specific implementation for a particular data type. This is useful when the generic template doesn't work correctly for a specific type, or when you want to optimize for a certain type. Here is a generic template. The display function template takes a value of type t and prints it to the console. Then we will see a specialized template for character pointers. The display function template is specialized for char pointers. This version prints a string label before the value. When you use the display function with an integer, the generic template is used. When you use it with a character pointer, the specialized template is used. Class templates allow you to define classes that can work with any data type, creating type-safe generic containers and data structures. Here's an example. The code shows a class template named pair that can store a pair of values of the same type, t. It has private members, first and second of type t, a constructor to initialize them, and a getMax function that returns the larger of the two values. Let's explore how to use class templates. Here is an example template with multiple parameters. The code shows a class template named dictionary that can store a key of type t and a value of type u. It has private members key and value of types t and u, a constructor to initialize them, and functions to get the key and value. Now we will look at how to use the templates. The code demonstrates how to use the pair and dictionary class templates with different data types. It creates instances of pair with int and double, and an instance of dictionary with string and int. It then calls the getMax function on the pair instances and stores the results in maxint and maxDouble. Templates can have default parameter types, making them more flexible and easier to use. Here is an example. The code shows a class template named container that takes two type parameters, t and u. U has a default type of integer. It has private members data of type t and id of type u, a constructor to initialize them, and functions to get the data and id. The constructor for container takes a value of type t and a value of type u with a default value of 0. Let's explore template constraints using C++ 20 concepts. Concepts allow you to constrain template parameters to specific requirements. This provides better error messages, clearer code intent, and improved compile times. Here is how to define a concept. The code defines a concept named numeric that checks if a type T is arithmetic using std is arithmetic v. Now let's use the concept to constrain a template. The code uses the numeric concept to constrain the template parameter T in the add function, ensuring that it only accepts numeric types. This is a simplified syntax. The code uses the numeric concept with the auto keyword to simplify the syntax of the multiply function, ensuring that it only accepts numeric types for both parameters. Let's summarize the template best practices. Do's: keep templates simple and focused. Use meaningful template parameter names. Provide clear documentation. Use constraints, also called concepts, when possible. Separate interface from implementation. Test with various types. Don'ts: avoid excessive template nesting. Don't overuse template metaprogramming. Beware of code bloat from instantiations. Avoid cryptic error messages. Don't assume all types will work. Avoid complex finding when concepts can help. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.